Signal processing, windowing, techniques for analyzing signals using specialized functions. Introduction to windowing, resolution and accuracy, window type and bandwidth. Windowing is a critical concept in vibration analysis and signal processing, particularly when using the fast Fourier transform, FFT, to convert time domain data into the frequency domain. The FFT assumes that the time waveform being analyzed is perfectly periodic and continuous. However, in reality, the captured time record often does not start and end at zero amplitude, which creates discontinuities at the edges of the sampled data. These discontinuities lead to a phenomenon called spectral leakage, where energy from a single frequency spreads into adjacent frequency bands, distorting the spectrum and making it difficult to identify true peaks. Windowing solves this problem by applying a mathematical function to the time record that tapers its ends towards zero amplitude, reducing the abrupt transitions and minimizing leakage. This process ensures that the FFT output more accurately represents the actual frequency content of the signal. Without windowing, the spectrum may show smeared peaks and false frequency components, which can mislead analysts during fault diagnosis. Therefore, windowing is essential for achieving clarity and precision in spectral analysis, especially when dealing with complex machinery signals where accurate identification of harmonics, sidebands, and fault frequencies is critical. Resolution and accuracy are two fundamental aspects affected by windowing in FFT analysis. Resolution refers to the ability to distinguish between two closely spaced frequencies in the spectrum and is calculated as R equal Fmax divided by LR, where Fmax is the maximum frequency and LR is the number of lines of resolution. Higher resolution means smaller spacing between frequency bands, allowing better separation of peaks. However, when a signal frequency falls between two bins, its energy is split, reducing amplitude accuracy. Windowing mitigates leakage but introduces amplitude errors because the tapering reduces the effective signal strength. For example, the commonly used Hanning window reduces amplitude accuracy to about 85% when the signal does not align perfectly with a bin. This trade-off is acceptable because the benefit of reducing leakage outweighs the slight amplitude loss. Analysts must understand that windowing improves frequency clarity but slightly compromises amplitude precision. Choosing the right balance between resolution and accuracy is crucial for reliable diagnostics, especially when identifying subtle fault signatures in rotating machinery. Different window types offer varying compromises between amplitude accuracy, frequency accuracy, and leakage reduction. The Hanning window is the most widely used in vibration analysis because it provides a good balance between reducing leakage and maintaining reasonable amplitude accuracy. It applies a cosine taper to the time record, minimizing discontinuities at the edges. The flat top window, on the other hand, is designed for applications requiring precise amplitude measurements, such as calibration, but it sacrifices frequency accuracy by spreading energy across multiple bins. The rectangular or uniform window applies no tapering and is suitable only when the waveform is perfectly periodic within the time record, such as in bump tests or modal analysis. Each window type has an associated window factor, WF, which affects bandwidth. The effective width of a frequency peak in the spectrum. Bandwidth is calculated as BW equals R times WF, meaning that applying a window increases the apparent width of spectral peaks. Analysts must select the appropriate window based on diagnostic goals, use Hanning for general machinery analysis, flat top for amplitude-critical tasks, and rectangular for controlled periodic signals. Understanding these trade-offs ensures accurate interpretation of vibration spectra and prevents misdiagnosis caused by spectral artifacts.